Welcome to the lab. Consider this explainer your definitive mission briefing on the extreme physics of surviving a black hole transit. We are going to look at the cold, hard science of what it takes to journey through absolutely the most hostile environments in the universe.
As a physicist, I look at the universe as this giant series of extreme equations just waiting to be solved. So I've got to ask you the ultimate question. Could humanity actually survive a black hole transit? If we somehow had the right technology, does the math actually allow us to thread the cosmic needle and come out alive on the other side? Well, we're going to find out.
Okay, let's dive right into this. Here's our flight plan for today. We'll start with the cosmic shortcut, look at engineering a traversable wormhole, meet our rotating behemoth, calculate the terrifying threat of tidal forces, explore the totally mind-bending reality of time dilation and radiation, and finally, deliver our definitive survival verdict.
Section 1. The Cosmic Shortcut. Let's look at the diagrams here. To really wrap our heads around how a black hole could act as a gateway, physicists use a clever technique called embedding. It helps us picture four-dimensional space-time in a way our brains can actually process. So this visualizes the Schwarzschild geometry as a two-dimensional surface embedded in 3D space. The mathematics of general relativity reveal this incredible, paraboloid-shaped throat linking two completely distinct sheets of space-time.
This whole setup, it's formally known as an Einstein-Rosen bridge. To the upper universe, it just looks like a standard black hole consuming matter and light. But to the lower universe, it theoretically appears as a white fountain, expelling all that same matter and energy. Now, while natural stellar black holes mathematically possess this feature, their actual radius is tiny, maybe only 30 kilometers across. Getting close to one of those would generate instant, lethal gravitational forces that would literally tear a ship apart long before it ever reached the bridge.
Moving on to Section 2. Engineering a traversable wormhole.
Since natural wormholes gravitationally collapse pretty much the second they form, we'd need to engineer a traversable one. And this flight plan requires three practically impossible steps. First, an unimaginably advanced civilization would need to grow a microscopic quantum wormhole. Second, they'd have to artificially prop open the throat using a massive influx of exotic negative energy. And third, well, we'd have to traverse it before it ultimately collapses. You'd basically need a civilization capable of manipulating time, events, and gravity on a galactic scale.
Back in 1988, physicist Kip Thorne and his students hit the nail on the head with this exact concept. They mathematically proved that wormholes laced with matter or energy exerting an enormous negative pressure could actually be stable and traversable. And here's the crazy part. Quantum mechanics actually allows for this. Specifically, certain energy states of the quantum vacuum, generated by something called the Casimir effect, can theoretically produce this repulsive tension, this exotic energy. You would need an astronomical amount of it, but theoretically, the math permits the door to stay open.
All right, Section 3. Meet the rotating behemoth.
Now, what's really interesting here is the stark contrast between these two types of black holes. A standard Schwarzschild black hole is non-rotating. It just has a central point singularity where gravity goes absolutely infinite. If you fall into that, you're dead. No exceptions. But a Kerr black hole, that is a fast-spinning monster. Because of its intense rotation, the singularity in the center isn't a point. It stretches out into the shape of a ring. And because it's a ring, you don't necessarily have to hit it. If you approach carefully, you can theoretically pass through or around it and actually survive.
The scientific literature on the Kerr metric is absolutely fascinating. When a black hole spins this incredibly fast, it creates an extreme environment dictated by something called the frame-dragging effect, or lens-theoring precession. The black hole literally drags the fabric of space-time around with it as it rotates. This drastically alters the geometry of the space around it, changing where a planet can safely orbit, and fundamentally warping how time itself behaves in that region.
Which brings us to Section 4, the threat of tidal forces.
Okay, let's talk about the Roche limit. When you get close to a massive gravitational body, gravity pulls on you based on distance. So if you're falling feet first toward a black hole, the gravity pulling on your feet is significantly stronger than the gravity pulling on your head. That difference is your tidal force. If you cross the Roche limit, that stretching force becomes stronger than the actual chemical bonds holding your body or your entire planet together. You stretch into a literal string of atoms in a visceral, terrifying process appropriately called spaghettification.
However, the math does provide a tiny loophole. The Roche limit depends on the mass of the black hole and the density of the object orbiting it. For a staggering 100 million solar mass black hole, a dense water planet can theoretically sit just outside the Roche limit without being torn apart. But make no mistake, the forces are still colossal. The equations show that tidal locking would occur almost instantly, within about 1 millisecond. The planet would be frozen in place, with one face constantly staring right into the abyss.
Section 5. Time dilation and lethal radiation. So, the absolutely crucial point here is this number, 99.999999998%. For a planet to survive on the razor's edge of the event horizon, the supermassive black hole must be spinning at exactly that percentage of the speed of light. It's this extreme, almost maximum possible spin that drags spacetime hard enough to stabilize the orbit of a planet that close.
And because the planet is orbiting so incredibly close and moving so fast through heavily curved spacetime, we experience extreme kinematic time dilation. The combination of your orbital velocity and the crushed spacetime geometry means that for every single hour you spend on that planet, 7 years pass for the rest of the universe. It's wild, but it's a mathematically sound concept that beautifully illustrates the elasticity of time in general relativity.
But let's put our physicist hats firmly back on for a second. Even if the gravity doesn't crush you, the neighborhood probably will. Supermassive black holes are surrounded by accretion disks, these swirling bands of superheated plasma. An active accretion disk emits extreme X-rays and gamma rays that would instantly sterilize any planet nearby. Now, if the black hole hasn't eaten in a million years, it might have an anemic accretion disk, cooled down to about 5,500 degrees Celsius. That's roughly the temperature of our sun, which saves you from the deadly radiation. But an anemic disk is transparent. It just wouldn't provide enough life-giving light or heat, leaving your planet totally freezing in the dark.
Section 6. The final survival verdict.
And this brilliantly illustrates our ultimate reality check. Could we actually make it? Well, preventing wormhole collapse requires massive amounts of theoretical exotic matter. The ring singularity of a spinning Kerr black hole, technically survivable. The crushing tidal forces can be survived, but only if the black hole is a massive 100 million solar mass behemoth. But the final nail in the coffin is that accretion disk. The radiation is either highly lethal or the environment is just too cold and transparent to support human life. The math of relativity technically allows the geometric journey, for sure, but the lethal physical reality makes survival practically impossible.
Which leaves us with a profound final thought. We've seen that the equations can bend, stretch, and contort spacetime to offer a razor-thin margin of theoretical survival. But given the catastrophic radiation, the crushing tidal forces, and the time dilation so extreme that literally everyone you ever knew would be dust before you returned, even if the math perfectly aligns to grant you safe passage, would you risk eternity to step into the dark? Thank you for exploring the warp side of astrophysics with me today in this explainer, and keep looking up.